Hi all. In this lecture, we are going to discuss the completeness property of a linear space. So consider a linear vector space with n dimension. So that means we'll have n basis vectors. Okay, now we are going to denote those basis vectors as phi. So phi 1, phi 2, up to phi n. Okay, so these are the basis vectors. Okay, so then if you take any other vector psi, we can expand this psi in terms of this basis vector. So the psi I can write from I equal to 1 to n ci phi I. Okay, so for the time being, we can choose this. The basis vectors are orthonormal. So what is going to be orthonormality? The inner product phi I phi j would give delta ij. Okay, so then take the inner product of psi with some phi j. So phi j with a psi would be the inner product phi j. What is psi? Sum over I equal to 1 to n ci phi I. Now, what we can do is we can take the summation outside. So how it is possible? Because this is nothing but phi j, comma. The sum is nothing but c1 phi 1 plus c2 phi 2 plus etc. up to cn phi n. So using distributive property, we can write this as phi j, comma c1 phi 1 plus phi j, comma c2 phi 2 plus phi j, comma c3 phi 3 up to phi j, comma cn phi n. Okay. Now we can use the linearity condition. Since this c1 is just coefficient, just a number which is multiplied with the post factor, it can be taken outside. So this can be written as c1 phi j, comma phi 1 plus c2 phi j, comma phi 2 plus etc. It goes up to cn phi j, comma phi n. Now this can be expressed as a sum. So sum over I equal to 1 to n ci phi j, comma phi I. Okay, so we have gone through a detailed steps, but we can directly write from here itself. Okay, instead of going to detailed step, what we can do is the inner product phi j, comma sum over I equal to 1 ci phi I can be, the summation can be taken outside in that inner product. So sum over I equal to 1 to n phi j, comma ci phi I we can write first. Then we can take ci outside. Ci is multiplying the post factor. So this can be sum over I equal to 1 to n ci phi I phi j. Okay, so indeed it is correct because we have shown in detail the final result is this. Now what is phi j, phi I? So according to the original assumption, according to our original assumption, this inner product phi I phi j is delta ij. So therefore, the inner product phi j phi I we can write as delta ij. So this would be equal to sum over I equal to 1 to n ci delta ij. Okay, now what would be the summation? So this delta ij would be 0 when I not equal to j, and it is 1 only if I equal to j. So delta ij is 1 only when I equal to j, otherwise it is 0. So if you submit the I from 1 to n, so only whenever the I become j, so it becomes only 1. So when and the I become j, it is delta ij is not 0. For all other terms, it's delta ij is 0. So that means it will picks up the value I equal to j. So this will give cj. So what was the left side? The left side was inner product phi j psi. The inner product phi j psi is cj. So we can write the expansion coefficient in this particular way. So then how we have written psi earlier? So psi we have expanded as sum over I equal to 1 to n ci phi I. Now we can write my ci's. This expansion coefficient I equal to 1 to n. Ci we can write as the inner product phi I psi. Phi I. So this is psi. Now, by definition, we can write the inner product as integral phi of phi star of x prime psi of x prime dx prime. So I have used a dummy index for the variable, and phi I is a function of x. So this can be written as sum over I equal to 1 to n integral. Okay, or this integral and summation are commuting always. So we can write integral of sum over I equal to 1 to n phi I star of x prime phi I of x times psi of x prime dx prime. And what was the left side? The left side is psi of x. How it is possible? So how we can satisfy this condition? So psi of x is integral of this quantity into psi of x prime dx should give psi of x. So what about this quantity? So we can just recall about the definition of Dirac delta function. So if you integrate f of x prime delta of x minus x prime dx prime, what will you get? This Dirac delta function is 0 whenever its variable is non-zero. Okay, so delta of x minus x prime equal to 0 when x not equal to x prime. So it has value only when x equal to x prime. So this integration would give, it will pick up the value of the function x prime equal to x. Okay, so this is the definition of Dirac delta function. This delta of x minus x prime is called Dirac delta function. Now, if you can compare these two equations, okay, so the left side is psi of x. So psi of x is the integral of some function into psi of x prime dx prime. So this implies that this summation, the quantity inside this bracket, should be a Dirac delta function. And only we should get psi of x. If you integrate psi of x prime over the mean index, then it has to multiply it with a Dirac delta function in order to get psi of x. So what is the result? So the result is sum over I equal to 1 to n phi I star of x prime phi of x must be equal to the drag delta function x minus x prime. So this is the another way of writing the completeness condition. Okay, so if a vector psi can be expanded as some ci phi I, where set phi I is a basis, then that basis said to be complete. That basis is said to be complete only if sum over I equal to 1 to n phi star of x prime, phi of x gives delta of x minus x prime. Okay, so this is a completeness condition of the basis. Okay, so this is enough for this particular topic, the completeness. Okay, so a basis vector, if you consider an orthonormal basis vector, this orthonormal basis vector is said to be complete if it satisfies this condition. So if the basis vector satisfies this condition, then we are sure that we can express any other vector in terms of this basis vector. That means this basis vector is complete. So that is what is the meaning of completeness. So once the basis vector is complete, we can express any other vector in terms of those basis vectors. Okay, if this is true, then this would be true. So here psi is any vector in that space. Okay, and I think we have to add one more thing. So, okay, so this is we should tell it is a unitary space. Okay, because we have to define the inner product. So in order to define the inner product, it must be unitary space. So a linear vector space with inner product defined is called the unitary space. Okay, so that is enough for this discussion. So we'll come up with the very important topic in the next class. So we'll introduce what is called the Dirac notation in the next class. So see you later. Bye.